Hello again, everyone. So today we're going to be talking about recursion, and I wanted to mention one or two things first. One, reminder that the project is due today. The second is I posted on Piazza and I pushed an email to everyone that I hadn't set the minimum on the timings quite high enough to prevent, perfectly good tiny test cases from being in under time. So I increased all of those to a slightly higher minimum. And I also modified our code to make sure that higher minimum goes into effect in the future automatically. So if you're having test cases that, like the really small ones, you were like 0.004 instead of 0.003, just resubmit them. Resubmit the code to the autograder and it'll redo it. It will get rid of the old ones that were blue because they aren't considered over time anymore because the limit has changed. So the web page just goes by the current limit. It has no idea what the limit was when you submitted. Okay, so talking about recursion, and we've looked at about recursion in the past, but never even gave a formal definition of it, that it is a function that calls itself. Now we could have a slightly different situation where function A calls B and B calls A, but we get the same effect of the function is effectively calling itself just indirectly through another function instead of directly. So if we have recursion occurring, and some of this you should have learned in 280, if we have recursion occurring, we have to have a base case. We have to have something that will eventually stop the recursive calls from happening. The other thing we need is each subsequent call has to have a simpler or smaller input. We have to decrease a number by 1 or something so that we are making progress towards that base case. It doesn't do us any good to have a base case when we reach 1 if we never reduce the size of the problem when we call the function. Now, when it says single recursion, meaning how many recursive calls does this function make? If we had something like a linked list, for example, we would often do single recursion where I say, well, I tried to insert it here, but I had to make a recursive call, and so I'll call insert with the next node pointer to try to insert it there. So that one recursive call occurring, whereas in trees, for instance, if I'm doing a tree traversal, I might make say for an in-order traversal, I may make a recursive call to in-order tree traversal of the left subtree, print what's in this node, and then make a recursive call to the right subtree. And that's what it means by multiple recursion. So we saw this question previously, the computing the power, x to the nth power, and we looked at a solution to it. And we wrote out a simple, straightforward linear complexity of x to the n is equal to x times x to the n minus 1 power. Obviously, we need base case. And that gets us one step smaller, got us big theta of m complexity. And then when we did the different definition, we got log n when we solved the recurrence relationship. Now, one thing about this one is we don't actually, in either of these, call it twice. We call it once, and then we take that value and multiply using it. The other thing was, and I sort of glossed over this, is when we did the recurrence relationship, we didn't consider these two different cases for the time, because one of them was just one more multiplication than the other. I could set my constant equal to the amount of work that happens in the larger case. So the constant would be greater by 1 when more work happens than when the extra multiplication doesn't happen. So not a big deal there to just have the constant be large enough to encompass either one of the recursive cases. So there's our two different functions, the linear solution and the logarithmic solution that we solved yesterday. And what we want to talk about now is a little bit more about tail recursion. So tail recursion occurs, again, when the recursive call has nothing pending. After the recursive call happens, a return can happen. And a function could be tail recursive even if it has more than one call to the recursive function, as long as only one of them could happen. So if I did something like, if I was doing a search in a tree, I might have like an if. If it's in the left, I return a recursive call on the left, else I return a recursive call on the right. And even if we get rid of the else, just the word else, this is still tail recursive because every possible path is tail recursive. Either I go into the if and go left, or I go right. Only one of them can happen. And when either one of them happens, the function is done. So this would be tail recursive, even though there are two calls, because at most one of them is going to occur. And obviously, we'd have a base case up above that. I didn't have room to fit it in this slide. Okay, so a recursive function that's not tail recursive generates an extra stack frame. So the stack frame has to contain things like parameters. What is being passed to this recursive function? It could contain things like local variables, return variables. We're going to look at a list of those in just a few slides. So we create those extra stack frames when there is a function that's not tail recursive. But when the compiler notices that a function is tail recursive, it can basically generate code that reuses the current stack frame instead of generating a new one. So nothing gets, the stack doesn't increase in size. We might replace some of the things on the stack with new ones, but we won't generate a whole new stack frame. So it involves less work and less chance that we stack overflow, that we run out of stack space. And there's a statement here at the bottom that says that tail recursion and iteration, meaning just using a loop, for loop, while loop, etc., are equivalent. So if you can write a tail recursive version of a function, it is possible to write an iterative version and vice versa. It doesn't mean that it'll be super easy, but it means it can be done. So as you become more comfortable with recursion, this equivalency is easier to achieve. So for example, we've got a simple function here, factorial, that just calls itself once. And if we look at what happens in main, so on the call stack, if we look at like inside of our Visual Studio debugger or Xcode debugger, there's a place to display. In Visual Studio, it's in the bottom right. On Xcode, I forget where it is. I think it's on the left middle pane, where you can have the view in that box show you the call stack. And so what we would see is main is on the call stack. And then it calls factorial of 5. I'm just going to write fact here, fact of 5. And then fact of 5 has a base case. It's got a recursive call, but it's not tail recursive, because after the recursive call is made, before the return happens, we have to do a multiplication. So factorial of 5 says, is this a base case? No. Well, I'd like to call factorial of 4, which calls factorial of 3, which calls factorial of 2, which calls factorial of 1, which calls factorial of 0, which then says, oh, I'm a base case. I will return the value 1 to the level above, and then this stack frame gets removed. And that 1 that gets returned gets multiplied by 1, because n is 1, and then we return to 1. Then this call is going to return a 1, and it gets removed. Multiply 2 times 1, return a 2. 2 times 3 is 6, return a 6. 6 times 4 is 24. Return the 24, and then 5 times 24 is 120. 120 goes back to main, and factorial of 5 gets popped off the stack. So that's the process that behind the scenes has to happen. Now, when we look at the call stack, and this is a slightly simplified view, and this is one of those things we're not going to put on the exam, but we like to give you the real explanation rather than half an explanation. So when we put things on the stack, things we have to save. So we have to save local variables. And you'd think, well, wait, local variables, aren't they in memory? Not quite. Because actually for variables to be part of an operation like a subtraction or a multiplication, they have to be inside of the CPU. And the CPU has a couple of spaces called registers. And every architecture has a different number of registers and different names for them, but they're named locations inside of the CPU that are used to hold things that are being used right now. And so those registers, because I don't know, when I call another function, I may not know what variables it's going to use, I might have to save all of my registers onto the stack and then call that other function. If it's a recursive call, then I know what registers are going to be reused. I can save only those. But if I'm calling a function other than myself, I have to save all of my registers to make sure that I get all of them back, because I don't know what that function will use or who it'll call and what registers it'll use. So we save our local variables onto the stack. We save any arguments. Things that we want to give that function have to go onto the stack. Another thing that has to go onto the stack here is actually where to return to in memory. Where do you go back to? Where does control return to in memory when the function is done? It goes on the stack also. So when that function call is received, it takes the arguments off of the stack. What does it do with them? It puts them in registers. Then it does its work. When it's done, it issues a return, and the return value has to go onto the stack. Then when we get back to, then we also have to grab that address off of the stack of who to return to. We go back to where we left off, and then when that return is received in the calling function, I have to say, oh, I've got to get that return value. I've got to put it in a register. I've got to take all the other registers I saved and restore those also. And the compiler will automatically generate code to make sure that when it puts this one in a register, it doesn't use one of the ones that had to be saved. It uses a different register so that we've got somewhere for that new value that was returned. And then we can restore all of our local variables off the stack. We can get rid of that return address off the stack, and then we continue on with our code. So all of those things happen behind the scenes. Now, when we make 6 nested calls, remember we called factorial 5 through factorial of 0, then there were 6 sets of local variables onto the stack all at one time. The parameters get pushed before the call and then popped when the call is received, and then the return value gets pushed and the return value gets popped. So those are transitory. The parameters get taken off and put in registers, or the return value gets taken off and put in register. But the registers that were saved for each call add up. And there's only one program stack. Well, not quite true. There's only one program stack per thread. If we were doing multi-threaded programming with multiple threads of execution all in one program, then there would be one stack per thread. But we don't do multi-threaded in EECS-281. You want to do multi-threaded, the 3 places I can think of is 440, design your own search engine, 482, operating systems, and 494, game design. And the 482 would be doing the lowest level stuff. 440, you would be learning how to use a thread library. 494, you'll use a whole development environment for games that has a built-in thread library. Now, the stack is a different place than the heap, where dynamic memory, where new occurs. So new occurs on the heap, and stack frames go onto the stack. The stack size is limited. If the stack size grows too much, then we've got what's called a stack overflow. And this happens commonly enough. Somebody created a programming question and answer website based on that name. So if we have a function that has a bug in it, a recursive function with a bug, it will exhaust the program memory, like if it doesn't make progress towards the base case, or the base case has a mistake in it. Or it could simply be, it's not a tail recursive function, and I called it with just too big a value. It's making progress, it's getting, n is going down by 1 every time, and there is a base case, but before we reach the base case, there's just too many recursive calls on the stack and it overflows. And I've seen anywhere from different operating systems and different numbers of parameters. The more parameters and the more parameters, the real thing is the more local variables you have, the faster the stack space would be exhausted. And so usually if you're passing like an integer, you can usually get at least 1,000 recursive calls in a non-tail recursive function. If it's tail recursive, who cares? We're going to reuse that stack frame over and over again, and we won't run out of stack space. Now, with our recursive function here, we've got a straightforward recursive factorial, and we've got a tail recursive function using something you may not have seen before called a default argument. So what we're saying is one of the arguments to this function has a default value. So if you call this, like back in main, I can call factorial of 5. When it receives that, when it receives that call, it'll say, oh, you just called me with one parameter, then therefore res, which is short for result didn't quite fit in the slide well, result gets a default value of 1 if you didn't specify it. If you do call it here with a value, then that overrides the default. So we call factorial of 5. Factorial of 5 says, well, I need to call factorial of 4 with result times n. So remember, result started out as 1. 1 times 5 is 5. And what this is basically we're doing the multiplication first. Now, could we have done this without a default argument? Sure. We could have made 2 factorials, a base version with 1 parameter that just calls the helper, and the helper has 2 parameters. But that didn't fit in the slide. We couldn't have fit the recursive and the 2 functions needed for the tail recursive in the slide if we did that, and this gives us a chance to show you default arguments. Okay, so what we're doing here is we're moving the multiplication to be before the recursive call, so that as soon as the recursive call is done, the return happens, and there's no intermediate calculations, so we've got a tail recursion. So factorial of 4 comma 5 calls factorial of 3 with 20, the multiplication as its parameter, which calls factorial of 2 with 60. I think, did I do this right? Let's see. Oh, wait. Nope, I'm doing this backwards. So 5 gets multiplied by 1. I should have kept track of result. So then 5 gets multiplied. I was not careful enough with this. No, factorial, no, that was right. I was right. Yeah, factorial of 60. Because we're doing it in a different order, I'm thinking the results are wrong. Okay, so factorial of 260 calls factorial of 1 with 120. And now that really is our answer, but we don't know that we're at a base case yet. We call factorial of 0 with the multiplication, 120. And then that recursive call realizes, hey, I'm the recursive call. I can return 1. I'm the recursive call. I can return 1. Or sorry, I'm the recursive call. I return the result that I've got so far. I was looking at the top version. I'm the recursive call. I'm a base case. I can return 120. And 120, then what happens is really these aren't all on the stack. These are actually replacing. The stack frame is getting replaced each time. This one says I can return 120 all the way back straight to main. The 120 goes straight back to main there. So that's how this one works. And you can, if you look in and run this with a debugger, the debugger will show you the different stack frames, but that doesn't mean they all exist separately. It's just showing, and not really showing stack frames, it's showing the history of the calls is what's displayed in your IDE. Okay, so our power function. So here's a tail recursive version of the power function. Now, first of all, did we really need this with log n complexity and log n recursive calls? Not really. Because, here's the reason why, because even if I ask for, let's say, 2 to the like 40th power, 2 to the 40th power, that would only require like a call stack of size 40. At most, right? And so if I ask for something larger, so I'd need log of 40. Log of 40 would be about 6 recursive calls. So I can't go up to, if I say, well, calculate 2 to the 1000th power. Even if I want the 1000th power, that's not going to be a lot of recursive calls, and I'd overflow an integer long before I reach that anyway. So to calculate 2 to the even millionth power would only require about 20-ish recursive calls. 2 to the 30th power, or 2 to the billionth power would require about 30 recursive calls. So not too bad in terms of the stack space. We're going to overflow the integers long before we have to worry about our stack space going over. So this one did basically the same thing as the previous one, multiply before you make the recursive call and make sure all the multiplications happen before the recursive call so that nothing has to be multiplied afterward. So we multiply x times x or result times x in the recursive call. So if I say, hey, I would like to calculate 2 to the 5th power. So x is 2 and n is 5. So I'd like to calculate 2 to the 5th. Is that a base case? No. Is it even? No. Okay, so it's odd, so I need x times x, so I need to make a recursive call with 4, comma 2. Oh, wait, there was a default here. Result, which was 1 to begin with. And now, when we make our recursive call, we would say, oh, the temporary result that you need is result times x, so you need a temporary result of 2. All right, so that one says, okay, I was called with n equal to 2. Am I a base case? No. Is n even? Yes. Okay, so I need to make a recursive call of 16, n times n. n over 2 is 1, 16 to the 1st power, multiplied by 2. The result just stays in there. All right, am I a base case? No, I'm not a base case. Is n even? No. Okay, n's not even, so I need a recursive call of x times x. This is where it gets a little weird. I need x times x, which is 256. For 256, then I need n over 2 is 0, so I need 256 to the 0th power multiplied by result times x, which is 32. Okay, am I a recursive call, or sorry, am I a base case in this recursive call? Am I a base case? Yes, because n is equal to 0, I'm a base case. Therefore, what I should return is result. 32 was the real answer. We calculated 256 without needing it. We already had the result, but we didn't know we were calling the base case. So we return 32, which goes straight back to the original caller, and yes, 2 to the 5th is 32. One of the things you should, just as a byproduct of being a computer science major, is learn your powers of 2. One thing I found hilarious a couple of years ago was I played a game on my phone of like connecting tiles next to each other that had the same value. And anyone remember the name of that game? It was one that had this interesting side effect of being written by computer science people, and 2048, and teaching people powers of 2, which I thought was just hilarious, that everyday people who don't use computers were learning powers of 2, like 2048, 4096, 8182, 16384, 32768, 65,536 is the end of my knowing them by heart, up to 2 to the 16th. Then beyond that, you get 2 to the 20th power is about 1 million. 2 to the 30th power is about 1 billion. And then just knowing those, I can say, hey, I've got a number that's about 1 million. Well, the log of that is about 20, because the log of 1,000 is about 10. 2 to the 10th is 1,024. So 2 to the 10th is about 1,000. The log of 1,000 is about 10. So you just sort of get used to those as you use them. Okay. Now, as we said, the program stack space is limited. Because the program stack space is limited, we can exhaust it if n is too large. With a large data set, simple recursion is dangerous. If I don't know that n is going to be limited, I've got to be careful about, maybe I shouldn't use simple recursion. I'm going to have to use tail recursion or write a function. Well, wait a minute. If I can't write a tail recursive version, how can I write it without recursion? Well, I could use a variable to keep track of where I am. Remember, the call stack is in fact a stack. So if I can't write a tail recursive version, I could still write it by using a stack or a queue as a local member variable inside of the function and loop over that queue, which is in fact what we're doing in Project 1. Now, in the queue-based approach, when the command line says -q or --queue, we couldn't write that recursively. We need the queue data structure. But you say, wait a minute, for the stack mode, couldn't we just make it recursive? Yes, but we're going to give you maps that are too big. We're going to give you maps that might have 26 colors and 5,000 rows, 5,000 columns. That's 25 million times 26, which would be 6.25 billion-ish. We can't have that many recursive calls. So you can't use recursion in Project 1 because even in the stack mode, you can't guarantee that you wouldn't overflow the stack. So this doesn't mean that everything has to be tail recursive. We may need the extra memory, but we can always use a data structure like a stack or a queue or something else to hold what we know still has to be done. That's basically what the DAC is doing in our Project 1. It's holding the things we know we still have to calculate. Okay, recurrence relations. So we can write out, and we said this in the previous lecture, we can write out a recurrence relation for the computation, for the time, for the memory. When we look at solving recurrence relationships, we wrote this one down last time and we solved it for the power function, which also fits the binary search function. So as you start seeing certain recurrence relations, you'll start knowing what the complexity class is without having to solve it because you've seen it often enough. And so here's some examples of common recurrence relations, which obviously have to have a base case, but we didn't need to say, hey, if they're recurrence, they got to have a base case of t of 0 or t of 1, doesn't matter which. So we've got this recurrence relationship. T of n is equal to t of n over 2 plus c. A common example of that is binary search, and it comes out being log n. T of n equals t of n minus 1 plus a constant is an example of linear search. If I've got n items and I'm looking for a value, if I don't find it in this location, well, I used to have n places to look. If it's not here, I now have n minus 1 places to look. It doesn't mean necessarily that I write linear search as a recursive function, but I can still write a recurrence relationship for it. And it turns out that we could write linear search with a loop, or we could write it tail recursively. Either way, the time complexity is going to be n. What about the next one? T of n equals 2t of n over 2 plus a constant. So that would be something like tree traversal. The 2t of n over 2 is I make a recursive call to the left half, I print this value, the other t of n over 2 is I make a recursive call to the right half. And so if I'm going to print everything in a tree, it makes sense that it should come out being a linear complexity if we solve that recurrence relationship. So I'm stating these up front. We haven't actually solved these yet. So if we took that one and solved it, we'd have O of n. Now we're going to learn how to do easier method coming up in another slide or 3. So then the next one, t of n equals t of n minus 1 plus c1 times n plus c2. So there's a non-constant amount of work after the recursive call, or after the recurrence relationship. So I reduce the size of the problem by 1, but I still have n work to do. So this is something like selection sort, where I say, oh, let's find the smallest element, smallest out of all n, swap it with index 0. Of the remaining n minus 1, find the smallest one, swap it with index 1. So I have to do that search. I have to say, of the remaining n minus 2, let's look at all of the remaining n minus 2 to find the smallest one, swap it with index 2, repeat the problem. So that's an example of selection sort, is an example of that recurrence relationship. Comes out n squared. And then if you look at merge sort, which I think you talked about in 280, quick sort, which we're going to learn this semester, and there's another sort that is also this complexity of n log n. So, what can we do to simplify these equations? We could do the substitution method, or we could learn the Master Theorem, which we're going to do coming up today. Now, if a recurrence problem, and this is the question of if I've got something like, this is the problem we had last time, is what if I cut it into 3 subproblems and I process 1 piece, 2 pieces, 3 pieces? Like if I have something like t of n is equal to 3t of n over 2. Or that should be n over 3. I forgot we're dividing into 3 pieces. 3t of n over 3, or 2t of n over 3, or 1t of n over 3. I could write all those down and solve them all out. What if there's an additional non-constant amount of work? It gets harder. So we'd like to not have to resolve those every time if possible, and that's where what's known as the Master Theorem comes in. So to use this theorem, we have to have a couple things true. So first of all, our t, time function, must be monotonically increasing. So what that means is that as n becomes larger, t of n becomes larger. It can't say, oh, well, if it's even, I do less work. Or sometimes the work flattens out. It doesn't keep going up, it just flattens out. So we have to have a larger n produces a larger amount of time for this to work. Then it has to be in a certain form. So our form here is we've got to have t of n equals a times t of n divided by b plus f of n, some function of n. We have to have a base case. It doesn't matter whether the base case is t of 1 or t of 0, as long as it's t of a constant. It could be t of 3, t of 2. We just have to have a base case of a constant amount. So we have to eventually reach a base case. And then we've got a few other rules. A has to be greater than or equal to 1. B has to be greater than 1. And then if all of those things are true, then, and also one other thing has to be true, f of n has to be of the form big theta of n to the c. Basically, it's saying this f of n has to be a polynomial function. So if that's a polynomial function, then we can do this. So what we do is we look at what is the relationship? How is a related to b to the c power? What happens with that relationship? Well, if that relationship is greater than, we get one form, equals, we get a second form, less than, we get a third form. So each of these different forms gives us a different complexity class. So what we want to do is go through some examples here, and we're going to repeat the equations, although you probably have the slides handy. You can refer to them. Whoops, no, I don't want to draw with my finger. I want to change slides. There we go. All right, so here's the first one. I've got everything on here. So we've got this one already written out. So I've got the equation up at the top. T of n equals 3t of n over 2 plus 3/4 of an n plus 1. Well, what are my parameters? A is the one out front here. B is the one that gets divided by. And then C is, this is of the form n to the first power. That's C. So we have to say this whole non-recursive portion is the form of a polynomial where C is 1. Well, then what we've got to do is, which condition are we in? How is A related to B to the C power? Okay, so I've got, whoops. So I've got, how is A related to B to the C power? Well, I've got, sorry, finger slip there. So we've got 3 is greater than, so I've got A, how is A related to B to the C power? I've got 3, how is that related to 2 to the first power? It's greater than. So if it's greater than, then it must have been, from the previous slide, it must have been that first case, big theta of n to the log base b of a. Now, one thing, I just noticed there's a slight typo in this slide. This equals should not be an equals. This should be an approximately equal to. So it's not really equal there, it's approximately equal, because that's an estimate of log base 2 of 3. And if we're saying big theta, we should be exactly right. And it's not exactly big theta of n to the 1.58 whatever. But the reason that we wanted to show you this last one is just to get an idea. Where is n to the log base 2 of 3? Well, it's bigger than n to the first power. It's smaller than n squared. So it's in between the two. But really, exactly, it is only exactly equal to this. It's only approximately equal to the last one. Okay, so if we go to the next slide, this was case 1. We go to the next slide. What I want you to do is take a minute, write them down, type them in the chat, whatever you want to do, and figure out what are our parameters. What are A, B, and C here? And then which one of the conditions is it? Is A equal to, less than, or greater than B to the C power? Okay, let's see what we got. Okay, nobody typed in the chat window yet. So we've got A. Well, A has to be the thing out front. So A must be 2 here. B is the thing we divide by, so that should be 4. Whoops, started writing B there, 4. And then C is, what is the form of this? Well, that's the square root of n, which is equivalent to n to the 1/2 power. Okay, so that's what we've got for our relationship. Then, what is A related to B to the C? So we want to know, how is A related to B to the C power? Well, that's how is 2 related to 4 to the 1/2, or the square root of 4. So 2 is equal to 2. So that must be the second case. So if it's the second case, then it's big theta of n of n to the C. So that'd be big theta of n to the 1/2 times log n. So this would be big theta of, we could also say big theta of square root of n times log n. Seems like a really odd complexity to reach, right? So that's one that would take a little bit of work to get there. Oh, whoops, I forgot the slide was animated and has those on there. Okay, so we've got that, so we conclude that we're in that final form. All right, I forgot the slides were animated because I stopped when I saw the right slide. Okay, so if we've got the last one here, if you're guessing that we had a greater than and equal to, and this one should come out being less than, good guessing. All right, so take a minute and look at the different parameters here. All right, so we've got A is equal to what's out front. Well, I don't see anything out front, so that should be a 1. B is what we divide by is 2. C is the power of this thing, should be, looks like a second order polynomial or a squared, so that's C is equal to 2. So we've got 1, 2, 2. How is A related to B to the C power? So how is 1 related to 2 squared? 2 squared would be less than. So we're in that third case, and we've got big theta of n to the C power, which is n squared. Now there's one thing about these that's not in the slide. So this was the sort of easy part of what is the application of the Master Theorem look like. What does the application look like? What we'd like to get a handle on is, what does it mean? What does it mean to be in the third case? What does it mean to be in, what does it mean to be in the third case? What does it mean to be in the second case? So let's go back to, let's stay on this one. This one's a good place to start. So we had this one, and we found that the third, because we were in this case, the form was big theta of n to the c. Well, that was just this part. This part was big theta of n to the c. What this is telling us is that the stuff that we did outside of the recursion was the bulk of the work. It was, remember, to say it's big theta of n to the c is the final form, that means it could have been big theta of n to the c plus some other stuff, like it could have been log n or something like that. The recursive, this is the recursive part. What it's saying is that the recursive part was no bigger than the non-recursive part. The non-recursive part was the bulk of the work. All right, let's go to the other end. Let's go to number 1 here. In the first case, we've got the C doesn't even come out in our equation. Our equation is big theta of n to the log base b of a. C doesn't even enter into this. So what this is saying is that the recursive portion was the bulk of the work. There wasn't much left to do after the recursion was over. It may not have been polynomial. It may not have been constant. It might have been slightly bigger than constant, but it wasn't as big as n to the log base b of a. So this one is saying the recursive part was the bulk of the work. Well then, if in case 1 the recursion is the bulk of the work, and in the third one the polynomial is the bulk of the work, then what's going on in case 2 here? Oops. Trying to find the slide on the tapping on it at the bottom. So in the second one, what we're saying is basically, because a was equal to b to the c power, just because we don't see a and b in there doesn't mean they're not in there. We've got big theta of n to the c log n. Well, how did we get the log? We got the log because we were doing recursion. We were dividing things into pieces. And the b and the a are in there. They're just components of c. So what this one is saying is basically the recursive portion and the non-recursive portion both contributed to the complexity of this one. They're both in there. So when the A is greater than B to the C, A and B are the bulk of the work. When A is less than B to the C, C is the bulk of the work, or N to the C is the bulk of the work. Otherwise, they're both contributing to it. So that's just sort of a feel for what this is telling us when we solve those. Okay, now there is a fourth condition. The fourth condition is one I would consider fair game for the lab exercises, but not for the exam. So the fourth one is saying, what if, or wait, sorry, we're not quite at the fourth one yet. I'm one slide too early. So we can't use the Master Theorem if T of n is not monotonic. So if T of n is like a sine function, weird in computer science might come up in another field. We can't use the Master Theorem. If f of n is not a polynomial, like if it's an exponential, we can't use the Master Theorem. If we can't express b as a constant, like T of n equals T of the root of something, that's not a division by a factor, so that can't be used. There is a fourth condition. So if these things don't hold, we can't use the Master Theorem, except for this special case, which I started to say is fair game for the lab, but not the exam. So, wait, we're not quite at the fourth condition yet. The other places we can't use it is where the recursion doesn't involve division. So if we have to be in the form of a T of n over b f of n. So the Master Theorem is not applicable if it's not in this form. We can't use it for subtraction. If there's T of n minus 1 or T of n minus 2, we've got to do substitution. So the fourth condition is, what if f of n isn't a polynomial, but it's something dealing with n to the power of something times a log to the kth power of n. So there's text missing from this slide. Let me look at I'm looking at the originals really quickly. Okay, wow, there's stuff in here that's not showing up in the PDF for some reason. So this should be k is greater than or equal to 0, and this should be k plus 1. I don't know why it's missing, because it is in the original PowerPoint, it's just not in the PDF. Okay, I'm going to have to remember to reproduce that PDF. Oh, and there's all this stuff. This is an element of big theta of big theta of is all missing from there. Okay, I'm going to have to remember to add to my to-do list. Edit these equations, republish the PDF. All right, so we've got this form. And what it means is, first of all, let's look at the log to the kth power. So when we say log to the kth power of n, this is equivalent to saying log of n to the kth power, which I should just reformat the slide like that. It'll make it a little bit easier to read, since we have to fix this slide anyway. So when we say log to the kth power of n, we really mean the log of n, that whole thing taken to the kth power. So if we've got something, if f of n is of the form n to the log base b of a, and those are the real b and a from the originally recurrence relationship, times log of n to any power, k doesn't matter, then our T of n is going to be of the form n to the log base b of a times the log of n to the k plus 1 power. So we have to increase the power. So like I said, this one, you might need it for the labs, but not for the exams. So, something for the exams. Hint time. When you take the exams, you're going to have open notes. Basically, anything we've given you during class that's on Canvas, slides, etc., you can use it. But you don't want to have to, during the exam, go, oh, wow, yeah, Master Theorem. I got to use the Master Theorem. Those were lecture 4 or 5 or 6. It was somewhere in there. Let's go load up that PDF and go paging through it. Start thinking now of what, if this were an in-person semester, what would be on your cheat sheet? start making a list. Electronically, it doesn't matter. Make a list of this has got to go on my cheat sheet, and before the actual exam day, write it down by hand. Write down by hand, here's the Master Theorem. Whatever else you decide has to go on that cheat sheet, because you don't want to take the time to dig through PDFs for something you could have been easily prepared for. So let's do an example of that one. And this one, I think it looks like all the symbols are present. It looks like nothing's missing from this one. Okay. So we've got a recurrence relationship here, 2t of n over 2 plus n log n. Okay, so a is 2, b is 2, that was easy. F of n is not a polynomial, that's obvious. But is it of the right form? Well, is it of the form n to the log base b of a? So n to the log base 2 of 2 times log of n to some power k. Is it of this form? Well, log base 2 of 2 is 1, so this means it has to be of the form n log n to some kth power, and it is. And k happens to be equal to 1 because we've just got n log n. So it's n log n, k is equal to 1, so our overall complexity ends up being n times log of n, the quantity squared. So there's an application of that one. All right, now here's a little thing. So suppose you've got a friend who's taking, say, 280 this semester, and they say, hey, I've come up with a great new way to find the maximum element in an unsorted array. It doesn't have to be O of n anymore. People have just totally missed it. I don't know how long, 50, 60, 70 years. They never realized that when we've got an unsorted array, we can still use this power of splitting things in half. So even though the array is unsorted, what I'm going to do is I'm going to split it into two halves. I'm going to find the maximum in each half, and then whichever one of those is bigger, that's the overall max. And that's going to split things in half, and it's going to be better than linear time. Okay. Now just a simple logical argument. If you've got an unsorted array and you don't look at all of the elements, you only look at some of them, how do you know you found the biggest one? If you skip even one of them, it could have been the maximum. Okay, your friend is not responding to logic, so we need math. So what's the recurrence relationship for this? Well, we've got T of n is our problem we want to solve, is problem of size n, is equal to T of n over 2 plus T of n over 2. So that's recursive call to the left half, recursive call to the right half, plus some constant amount of work for the taking the maximum of those two values. Okay, well that's equal to 2t of n over 2 plus c1, and hey, we can plug this into the Master Theorem. A is equal to 1, or sorry, 2. A is equal to 2, B is equal to 2, C is equal to, it's not C1. This thing is of the form big theta of n to the 0th power, so C is equal to 0. So how is A related to B to the C power? Well, 2 is greater than 2 to the 0th. If 2 is greater than 2 to the 0th, then we know it's of the form big theta of n to the log base B of A, which is big theta of n to the log base 2 of 2, which is big theta of n. So our intuition, you can't find the maximum by skipping some of them, is true. All right, so what we're going to do is look at a problem here that we want to solve and look at some recurrence relationships. So this is an old interview question. So the question is, they give you this table of values, and they say there's this two-dimensional array with n is the number of rows, m is the number of columns. So you've got this n by m two-dimensional array, And they tell you everything is sorted by rows and columns. So when they say something is sorted by, so the condition table ij is less than or equal to table ij plus 1, that's saying basically, remember the first dimension, this is, in our indices, this is the row, and this one is the column. That's a standard sort of way of thinking about two-dimensional arrays. So the first dimension is the row, second dimension is the column. So we're saying something in this row and column has to be less than or equal to something in a column to the right of it. So everything has to be less than or equal to the things to the right of it. Second rule says everything must be less than or equal to the thing below it. So this table doesn't have any equal values next to each other, but we could picture it like, hey, say this 8 was actually a 5, that would still be, oh wait, no, that would be invalid because then there's a 7 above it. Okay, if that was a 4, so if that was a 4 and a 5, then we'd have duplicate values next to each other, and the columns would still be sorted. So that would still be meeting the rules of this problem. So that's what they gave you, is those are the rules of the problem. What we want to do is, what's the complexity of finding a particular value? So it says searches for a value. So we're searching for some value, like let's say 13. How could we find 13? Well, obvious ideas, we could do a linear search of every row. That would be n times m complexity. We could do a linear search of every column, would be m times n, still the same product. I could do a binary search of every row. So every row, every one of the n rows, I do a binary search on every row. I could do a binary search of every column, which would be m times log of n. And my claim is that's still too slow. We got to do better than that. So if you can at least remember the other thing about interview questions, if I haven't said it before, is the point of every interview question is not necessarily getting the best answer. The point of a lot of coding problems and interview questions is, can you avoid the obvious mistakes? Can you jump to somewhat more efficient than obvious quickly? Can you explain how you got there? Companies have room for a limited number of people who can always get the right answer but can't communicate with human beings. They have a limited number of job openings for those people. Most of the people they want to hire can communicate with other human beings and work in a group. And so a lot of these questions are not about necessarily did you get the best possible answer, as could you explain why you avoided the obvious mistakes? Could you explain why the approach you have chosen will work? And maybe you say, well, I think maybe we could do something better than this, try something like this. I don't think I have enough time to prove to myself that it's going to work, but it would be better time. But I'm not sure we'd get the right answer. And we'd have to do more thinking about that. That would be a great answer for a problem. Even if you don't have the most optimal answer, you've still been able to explain how you got to your solution and what your reasoning was. Okay, so my claim is we're still too slow, even at n log m or m log n. So what we're going to do is we're going to say, hey, let's divide it up. Instead of dividing it into rows, let's divide it into 4 regions, right? Let's cut it down a vertical and horizontal axes. Let's cut it into 4 regions. And what I can do is, if I'm looking for a certain value, I can eliminate one of the regions. So I split it basically down the middle, and this was 5 by 5, so it wasn't quite down the middle. There's 3 in one dimension, 2 in another. But if I look at this middle value, let's say I'm searching for the value 13. Well, I know it can't be in the upper left. Because if it was in the upper left, it would have to be, if it's left of 9, it has to be less than or equal to 9. If it's above 9, it's got to be less than or equal to 9. And everything, if these all have to be less than or equal to 9, and those have to be less than or equal to 9, then that rule applies in every row and every column. Everything up in the upper left must be less than or equal to 9. So if that was the case, I could eliminate the upper left quadrant. What if I said I'm searching for the value 4? Well, it can't be in the bottom right. 4, there could be a 4 right there. It could be in the bottom left. If these were both 4s, it could be in the upper right. Or if this was like 2 and 2 and 4, it could be in the upper right. It could be in the upper left. But 4 can't be down there. So given the value being greater than or less than the center, I can eliminate one of those quadrants, either the upper left or I can eliminate the upper right. One of them is going to go, and then I can recurse into the other 3. So that gives me the recurrence relationship. Now here I'm writing it in terms of n. N is the length of one side. And I made a simplification here to get to one variable instead of 2. I'm assuming that basically both sizes are size n. Because we can see when we start splitting it into pieces, it's not going to stay n over 2 and m over 2 anyway. But it'll be approximately n over 2. So we simplified it a little bit. Let's get rid of the 2 different variables. Let's make one variable, and that variable is the length of a side. So if I split it into 4 regions, each region would have 1/4 of the original members, but the size of the side would be cut in half. So I've gone from like 5 by 5 down to things that are around 3 by 3 or 2 by 2-ish. Well, we could take that, plug it into the Master Theorem, and solve it. We're not going to solve all these yet. We're going to present the equations for different approaches. So there's one way we could do it. Okay, now what if I say, hey, let's not check one value in the middle. Let's check all the values in the middle. Let's find out if the value's in the middle column, and if it's not, I'm going to be able to eliminate 2 regions. So I'm looking for 13, and what I really want to find is not where it is, because it might not be there. If I get lucky, I'm searching for 8. I find it, great. But if I'm searching for something like 13, what I want to know is where it should be. So what we do is we look in that middle column. I can say, hey, let's do a linear search down that middle column looking for 13. Not it, not it, not it. Too big. 13 should be there. So that's where it should be. So what I'm going to do is I'm going to look at the values just above and below where it should be, 9 and 14. Okay, well now I know. Everything in the upper left is less than or equal to 9. Everything in the bottom right is greater than or equal to 14. It can't be in either of those. It's got to be in one of the other 2 regions. And then we do it again. Do it again, do it again, do it again. So we can write a recurrence relationship for this. We can say T of n is 2t of n over 2. I've got 2 regions. I cut the size in half. I recurse into 2 regions instead of 3. But I only had to do a constant amount of work to scan down that middle column. Oh, wait a minute. I don't have to scan down that middle column. I could improve that by saying, what if I binary search the middle column? I could binary search that middle column, and then instead of plus n, cn, it'd be plus c times log n. All right, so now I've got 2 different equations there. We would need to solve those. Does this one? Oh, this one looks like it's not in the form of the Master Theorem. Does it fit option 4? Maybe we'd have to look deeper at that. So we could, if we use the Master Theorem or substitution on each of these, we get the quad partitioning is, hey, and it's got the equivalently, approximately equal in this one. So we get the 3t of n over 2 plus c, big theta of n to the log base 2 of 3 is about n to the 1.58 power. That one that seemed so weird, n to the 1.58 power approximately, turns out it's an actual equation for an actual algorithm. All right, what about if we binary partition? Binary partition means what if we did a linear search of the middle column? And really, it could be the middle row or the middle column. We could reverse it. We could do middle column and update, and it'll still eliminate two regions. We could do a middle row, middle column, doesn't matter. So that's the binary partitioning. The improved binary partitioning, that's just getting rid of that sloppy I there. The improved binary partitioning is, what if we do a binary search of that middle row or column? We get, instead of big theta of n log n, we get big theta of n. Wow, big theta of n, that's pretty good. We've got n times n items, but I only had to check n of them to find it. So that's the improved binary partitioning. So if we binary search the middle row or the middle column, we can get it down to big theta of n. Now, what about a different way to do it? Here's a completely different way, and this one we provided full code for it. The idea is, I'm searching for a value. Okay, so what have we got here? Let's look at our parameters. We've got a Boolean, true or false, stepwise, so that's the name of the function, stepwise linear. We've got a matrix of size, I don't know, and n. N would have to be known up front. N would have to be a named constant for this to work. N would have to be a named constant, or else we can't make this work with. I suppose if we'd been willing to put it in a couple lines, we could have said, we could have put a 2D vector in there, and then we would have known each size exactly. Anyway, didn't quite fit in one slide that way. So we've got our matrix, n is a named constant, m is a variable. We've got a target. The target value is what we're searching for. Like, I'm searching for 13. And we're given row and column by reference. Okay, we'll get back to those. It says, okay, so what is the first if doing? It's saying if the target is less than matrix 0, 0, or the target is greater than matrix m-1, n-1. So it's saying if it's less than this value or greater than that value, say false. Ah, we've determined it cannot possibly be in there. So that's lines 2 and 3 is saying it just can't be in there if it's that small or that big. All right, what about line 4? Line 4 says let's start at row 0, column n-1. We've changed the parameters. These were passed in by reference, so we've said let's start at row 0, column n-1. Let's start here. So we're starting in the upper right, and then let's look at what it does. It says, okay, while our row number is valid and our column number is valid, okay, so while we haven't stepped off the edge of the matrix, if matrix row column is less than the target, then change the row. Okay, so our target, let's say we did a target of 13. So is matrix row column less than 13? No, it's greater than. So let's change the column. So what we're saying is, hey, I'm looking for 13, and when I see a 15, I know it can't be below 15. I've got to go back to a previous column. It's got to be somewhere to the left of 15. It can't be below it. So I can move over there. So now I'm looking here. I'm saying, hey, how do you compare to 13? Are you less than 13? Oh, you are. Well, if you're less than 13, that means 13 can't possibly be to the left of you. Let's go down a row. So we're at 12. So we say, okay, we're still in the bounds of the array. Is this value 12 less than the target? It is. Well, then 13 can't be over there. Let's move down to here. Okay, is that value less than the target? No. Is it greater than the target? Yes, it is. So the target value, 13, can't be there. Let's move over to here. Is that value less than the target? Yes, it is. Let's eliminate everything to the left of it. Let's move down. Got to be here. All right, well, it doesn't got to be there, but it's got to be in that region. Okay, so we say 14. Are you less than the target? No. You are greater than the target, so we change the column number. So it can't be here. Let's move there. Aha, we found the 13. And if we were searching for something like what's not in there, 12, 13, 14, 16. 19, 18. Lots of values are in there. 19, 20, I guess. Yeah, if we were searching for 20, we wouldn't find it. If we were searching for 20, we'd eventually fall off the edge somewhere. So we find 13, we return true, and when we return true, right now, row, the value row is 0, 1, 2, 3. Row is now 3, and column is now 1. So we return true. If we return true, the caller knows these are valid to look at. If we return false, the caller knows, hey, those aren't valid to look at because it was never found. So this one is one that I would say, wow, I don't really want to write a recurrence relationship of this complexity. Let's logic this complexity out. So what's the most amount of work I can do? Well, I can go n-1 times I can move left, m-1 times I can move down at most. Like I could go left 5 times and fall off the edge, but I could go left 4 times and down 4 times before I fall off the edge. So the complexity of this is at most. So my best case complexity would be O of 1. I was looking for 15, found it in the corner, I'm done. But my worst case complexity could be as bad as n-1 plus m-1, m-1 plus 1. So I could move left down n-1, n-1 plus m-1 times, plus 1 more time, I fall off the edge. If I go back through the loop 1 more time, I'd be falling off the edge. So that's how many times that loop is going to run, which is approximately big theta of n plus m, which if we only had one variable would be big theta of m if both sides were the same size. So this one is linear complexity also. Now, let's look at, could we use this same approach slightly differently? So let me just erase most of the marks up here where I drew over the top of our table. Okay, so we started, the code here started in the upper right. Could we, if you change the code a bit, could we start looking for 13 in the bottom left? Could we say, hey, are you a 13? No, you're not, but I know it can't be to the right of you. It's got to be above you somewhere. Either above you directly or above you and to the right, but it can't be straight to the right of you. All right, so let's move up. Are you a 13? No, you're too small, so it can't be above you. It's got to be somewhere to your right. Aha, we found the 13. We got there a little faster from this direction, but we got there. All right, so if we change the code, if we change like the while condition and the if statements and the what I change my variables to, with a little bit of minor changes, and change my initialization. So basically, if I change lines 4 through 9 a little bit, we could start in the bottom left. We'd still get the answer. What about, could we start in the upper left? Could I start here and say, hey, are you 13? No, you're not. Well, what can I eliminate? The place I looked. Because 13 could be down there. That 18 could be a 13. It could be to the right of me. That 15 could be a 13. The 11 could be a 13. So I can't eliminate anything if I start with the smallest value or the largest value. I only get to eliminate one value. I don't get to eliminate a whole row or column. So we can't start in the upper left, can't start in the bottom right, but we can start here or we could start there, and then decide it's either got to be move right, move left, etc. Or depending on where we start, we can change the column or we can change the row and get much closer to a solution. All right, so someone took all of these and implemented them. Oh wait, I forgot that it was animated. We had that in there. Okay, so someone, and we got links in here, did all of these things and looked at how it could go. So the binary search is basically like they didn't even do. So they did m and n were equal to 100, so 100 by 100, and they did 1,000,000 searches. So they took this filled it with random numbers that met the conditions, and then they searched it, and they only timed the searching part. They didn't time the filling the arrays part. So they didn't even do the let's just do a linear search of every row. That was just off the table. So they said, what if we do a binary search of every row or every column? Comes out 31.6 seconds. Diagonal. We could actually do this diagonally. It turns out to be it's still the same thing. Like I could binary search every diagonal because of the rules would allow it. I can binary search every diagonal, but that turns out to be a little bit worse. It's still the same theoretical complexity, like n log n, but it's worse because the cache gets used less well. And I'll explain that in a minute. The stepwise linear, the one we just did, which was, remember this one was big theta of n, came out about 10.71. The quad partitioning is 17.3. The binary partitioning, so that's the what if we binary search, or sorry, this is what if we linear search the middle row, and the improved is what if we binary search the middle row. So the binary searching the middle row or middle column turns out to be the best way to do it. Both of these were big theta of n, but one of them comes out better timing than the other. Why? Two possible reasons. One is slightly better constants, right? The improved binary partitioning could have slightly better constants in it, which makes it run a bit faster. The other thing is the cache. And I'm going to explain this to you. It's going to be important to understand why we do things the way we do them, but it's not going to be on the exam. So the cache is, and I think I explained this last week, I think. The cache is when you want to run a program, things have to be inside of the CPU. But I've got my main memory, like I've got a machine with like 16 gigabytes of RAM. So that's my DRAM. And then up here is my CPU. The CPU runs at CPU speed. The DRAM runs, let's say, 100 times slower. If I want to do an operation on something and it's not in the CPU, I have to go out to the DRAM, and the CPU might have to twiddle its thumbs while it could be doing 100 calculations, 100 additions, 100 if statements. Instead, it's just sitting there waiting for something to be loaded from the DRAM. So years ago, computer architects decided, hey, we gotta speed this up. As CPUs became much faster than RAM, we had to do something about it. So what we did was we put in the middle here a cache. C-A-C-H-E means a place to store things. The cache runs at close to CPU speed, like same speed, 1x or 2 times slower, say. So it runs at really close to the CPU speed. Another thing that they found, this would help you in getting things into the CPU faster, but it's not going to be as big. Like where this might be 16 gigabytes, this might be 1 megabyte. Because it has to fit inside of the CPU, it's got to be fast. We've got a little bit of more limitations on space. We can't store everything in there, but we can store things that we've used recently. But it still doesn't help us when we still have to go to memory. Things are slow. So what they found is that when you go to grab something from the RAM, where it might take, let's say, 100 cycles to get one thing, it might take like 108 cycles to get 8 things if they're all adjacent. So when we get what's called a cache miss, what I want is not in the cache. The cache goes and grabs from DRAM, but it doesn't grab one value. It grabs one value and like the next 7 values adjacent to it, it loads 8 things into here in what's called a cache line. So then if we look at how programs behave, they take advantage of this. Programs exhibit what's called locality of reference. What that means is that if you look at index 0, where are you most likely to look next? Index 1. Or if you looked at let's say index 10. Where are you most likely to look next? Either index 11 is very likely. Index 9 is pretty likely also if you like moving left through the row, like with the stepwise linear. So either way, if the one to the left of me is not in there, don't just grab the one to the left of me, grab the one to the left of me and the 7 that precede it. They're all in that same 8 bytes of memory or 8 words of memory or whatever it is. Grab them all at once and get them into the cache. So because computer programs exhibit locality of reference, programs that do that, programs tend to do that, the programs that do exhibit that locality of reference make better use of the cache and perform better. So what we'll see here is if we do like the improved binary partitioning, if we do it intelligently, the best way to do it would be let's binary search the columns, but then let's eliminate them and do or maybe it would be better to binary search the rows. We'd have to think about it. Probably binary search the columns would be better. Anyway, if we take advantage of the cache, we'll get better performance. And that might be another reason for this discrepancy. Even though they're both big theta of n, maybe the stepwise linear just doesn't use the cache quite as well as the improved binary partitioning. So that's why in Project 1, we told you you have to do your 3D vector in the order colors, rows, columns. Because think about when we print stuff. When we print stuff, we've got to go through the rows and the columns. For each row, I go through the column. I want to, when I'm within a row, everything is adjacent in memory, and I take advantage of locality of reference. So this makes your program faster. Putting your indices in this order makes your program faster, and it saves memory because colors could be much less than rows or columns, like 26 at most, 27 at most, compared to like 1,000 or 5,000. We save memory. Okay, we're over by like 2 minutes here. Let's call this done. And yeah, someone said it's guessing what you want. It's guessing what you are likely to do if you are the average program. Yep. It's not guessing what you will do. It's guessing what the average program is likely to do. And that's what we speed up is most programs. All right, let's call this done. And we'll everybody get some lunch and we'll see everybody back in Prof's hours in like 38 minutes.